Okay. Okay. Oh, yeah. Okay. Okay. Uh, so we have these solutions. Let me show you some examples. It's easier to show example than rather than show this. Okay. Now, finally, control gain. We know control gain is FC equal to minus R inverse B C transpose P. Riccati equations is AC transpose B plus PAC minus PBC R inverse B PCT P plus Q equal to 0, and P must be positive definite. That means it must be larger than 0 such that the cost index larger than 0. The control force U equal to FCX equals to minus R inverse BC transpose PX. That's FC here. So that's my F. That's my U, control force. That's the control force. As soon as you solve these Riccati equations, then you got a P. BC is input matrix. R is the weighting term that you give to that. Normally, Q, we use the identity matrix. Okay, that's the formulations for the Riccati equations. Let us look at example. The example we used earlier. Single state. A equal to A, BC equal to B, R equal to R, Q equal to 1. That's, so Riccati equations, just like that. That's my Riccati equation. You sub into that Riccati equation and put them together, then you find out P here. P square equal there, plus 1 equal to 0. All right? Then solve for P. Then you got this. Solve for P. P square here. So solve for P, then you got that two solutions. Plus or minus. But we know P has to be positive. We know that. Also depend on A. So if A less than 0, the constant P and the control gain become, because P has to be positive. All right? So if I do this, then 1 plus this square, this 1 plus B square is positive, A square positive, R is positive, so this will be less than 1. So you have to choose minus. All right, and then that's larger than 0. Then F will be equal to, if you choose negative, if you choose positive, then you got a problem. All right, because P is negative, A is negative, and this 1 minus square root of that is the whole term is negative. So negative part times A negative, P is positive. Right? Now if you choose positive, then this is positive, then A is negative, then P is negative. So, oh good. P has to be positive. So if I choose this P equal to that, then my F equal to that. And this is exactly the same solution we got earlier. When R going to infinite, F equal to 0. Right? If R going to infinite, F equal to 0. Because if this going to infinite, this become 1. 1 minus square root of 1 equals 0. So F equals 0. For this simple example, any questions? So that proves that my Riccati equation here is correct. at least for single state. All right, so A plus BF has to be always whole for A less than 0 because BF less than 0. Right? It depends on your B. So BF, you time BF, B square P over R, and P is positive, so BF is always negative. Agree? So A plus BF always negative, because A negative, and also BF negative. So A plus BF always negative. That's true too. So that satisfies my existing conditions. All right. Now let us look at another example. This airplane in horizontal cruising. Equation of motion is the psi, that's the perturbation from cruise angle of attack. Phi, that's perturbation of cruise pitch angle velocities. All right, and then tau is we call lifting time constant. Well, we don't have to understand about this. But this is a real example. The omega is and then the pitch natural frequencies. So how can you find the F and U? Such that the U is we call elevator deflections. So that U. And when you control the elevator, then you will be able to control your cruise angle and your perturbation of the cruise pitch angle velocities. So determine steady state constant F1, F2 such that I want to mean such that U F1, F2 is F1 multiplied by this side plus F2 multiplied by phi. I want these solutions. That's my state. Psi and phi is my state. That minimizes. Okay, watch this. My minimization is psi square plus phi square plus u square. Now from here, you must figure your own R. How much for R for this? 1. How much for Q for this? Okay, that's what we need to. So that's the state space form of that one. All right. My Riccati equation is for this one, where R equal to 1, QC equal to 1, 0, 0, 1. Because my cost functions is this, psi square plus phi square. I have a long state. I don't have a couple between psi and phi. Right? Just like what I say, most of the time we always assume QC equal to 1, 0, 0, 1. Those are what I call identity matrix. So I equal to 1, BC is 0, 1. That's so you had to based on these two equations and form your matrix equations. Form that matrix equations. So that's the matrix equation in form from the two equation of motions. So my Riccati equation is AC. That's my AC. P plus AC minus P BC. BC is this guy 0, 1. R inverse is 1. BC is just transpose P T plus Q, and where that equal to this. Any questions? So when we got this Riccati equations, then conjugate gain will be that. Now we have to solve these Riccati equations. And this is the F1, F2 equal to BC transpose P. Any questions about this? It's very simple, right? Okay. Now I'm going to solve Riccati equations. Now P equal to P11, P12, P12, P22. And the recurring equation, you sub this P into that recurring equations, then you will find out you have 3 equations you have to solve P11, P22, and P12. Okay. Any questions? No? Okay. All good? Control gain will be minus 0, 1. R inverse is R equal to 1. And this is my PC, transpose. P11, P12, P12, P22. Matter of fact, I need to solve only P12 and P22 because this multiplied by that is P12. This 0, 1 multiplied by P12, P22 is minus P22. So from these 3 equations, I need to solve P11, P12, and P22. Okay, how much I solve? All right, consider, say tau equal to 1, omega equal to 1, then I have a solution P, 1, 1, 1 minus square root 3. I have second solution, 1, 1, 1 square root 3. I have 30 solutions. That is my third solutions. And I have my fourth solution. I have to do 4 solutions. But only one solution is right. That one has to be what? Positive definite. And they're all symmetric. So which is the right one? One is positive definite. It's very simple to see. Any positive definite matrix, their diagonal element always positive. So if you have one diagonal element like this minus square root 3, good. This won't be positive anymore. Definitely not. So you have negative here, that is no good anymore. Negative here, negative is no good anymore. All right. Only here, where diagonal is 1, all diagonal is positive. 1 and square root 3, and is this good solutions? And we have to prove it. You can solve the eigenvalue of this guy, see if their eigenvalue are positive. So that's the only solution you got. You will never ever get 2 solutions, 2 positive definite solutions. That's the theory. The Riccati equation only gives you one solution. That solution is positive definite. So when you use the software to solve it, the solution they give to you, that has to be positive definite. They don't give you any other solutions. All right. So my control gain is minus P12 minus P22 equals parentheses minus 1 minus square root of 3. That's it. That's the solutions. So when you, of course, now when you try to design an optimal control, you don't solve the way I did. That's only you can solve 2 by 2. For 1 and 2 by 2, 3 by 3, 4 by 4, good luck. Yeah, he may solve for a lifetime. And the computer, they develop algorithm to solve this equation, Riccati equation. Not like that either. They have a special way to do it. Very nice and clean. Very nice methods to solve this. So that is the optimal control. All right. So these chapters, we minimize the cost index to obtain an optimum 4-state feedback controller. Four-state feedback controller. You know that. Because that means we need observer. We need state estimator. When you use this controller, optimal controller, you need the observer. I already showed you in the first slide, right? Because your U equal to F X hat. When you really try to use this method, you gotta replace that X by X hat. Okay? So now, but the problem is determining state and control weighted matrix Q and I is a practical issues. You need to try. Sometimes, most of the time, we just try and error. Because you are, if we assume we Q equal to identity, you are too small, then your control force may exceed your maximum control force you can provide. If R is too large, your performance may not be good, may not be good. Remember that if R is infinite, then your gain, your F, is equal to 0. The gain in manifest is all equal to 0. That's not good either. That means you have no performance. So Q and R is a really practical issue. In the past, well, in my days in the 80s or 90s, there are many different methods to try to design R and Q for you. And as a mechanical engineer, they prefer to use the energies because I can minimize my system energies, I can minimize control energies. So Q and R, they are related to the energy mass matrix and stiffness matrix. That's what most of the cases for mechanical engineering. It is applicable to continuous time and discrete time for all those models. The discrete time Ricardo equation is a little bit different, but form is very similar. It's also solvable. However, now if a matrix is 1,000 by 1,000, then you try to by 1,000 by 1,000 state matrix, you try to apply optimal control, you might have a numerical problem too. All right, because solve Ricardo equation is a nonlinear equations. Ricardo equation is a nonlinear equations. To solve a nonlinear equations, you gotta be careful. Even you have a very nice method, you still may end up some numerical error involved. Okay, that's the optimal control, chapters. And that's all finished with optimal control. However, optimal control can be a book. This is on a very small set. This is on a very basic. The optimal control, the index doesn't have to be infinite. Right? Can be some fixed time. So the control index, a lot of different ways to define the control index. You can have a terminal control too. Terminal control means you have a terminal state also included in your cost index. All right, but this is the basic concept I can introduce to you. That's what's going on for this. And now I'm going to go back to something the matrix fundamental for a few minutes, and I talk about a little bit more on that, so you can, because all this is all matrix. So you understand a little bit better about matrix fundamental, right? Then I go back to that matrix fundamental, so I can spend a little bit of time. We still have a little bit of time to do that, and then I'm going to the let me go back to the front page, because that's important. A lot of important metric theory that you gotta understand a little bit more. Because I skipped the I did not really talk about matrix theory. I supposed to talk about matrix theory in the very early time, and so let me go back to the front page because I want to show you some of basic sense. Okay, let me. We already talked about a little bit the matrix pseudo inverse. We talk about least square. I didn't talk about the minimum norm solution. That's a control method. We normally we don't do that. So I want to talk about this really simple equations, linear equations. That's only one single linear equations. How many solutions we have for this equation? How many solutions we have? For x1 and x2, how many solutions do you think we have? Any idea? Many solutions for x. Because what? This is more unknown than equations. All right, for this one, do we have any solutions? Or how many we have? Only one. We got unique solutions. We got two equations, two unknown. How about this? How many solutions we have? No solutions. We have one equation, two unknown, or no solutions. No solutions. How about this? This is 5, 6, this is 5, 10. Many solutions. Because these two equations are not independent. So you have many solutions. Although you got two equations, but you got only one, you really got one equation. So that's something that very simple the review or refresh your memory for those we call linear equations. And this is the basic metric theory for that. All right. Now, unique solutions. There's unique solutions. So, for unique solutions, what is the solution? That means these two lines and they cross. So you have two lines, one line representing one equation, another line represents another equation, represent another equation, and you have somewhere there that they cross. So x1 equal to 3, x2 equal to 1. Now, it's called optimum solutions. This is related to optimum control. The linear equation like this, that's only one equation. And you have so many unknowns to satisfy with that. So sometimes what we do, we minimize the linear sum. So we give them a call like an index. I like to find a solution which minimizes x1 absolute value plus x2 absolute values. So within that many solutions, I want to find a solutions. That solution minimizes the x1 absolute value of an absolute value x2. So this is more like our cost index. Or we minimize the discrete sum x1 square plus x2 square. Because our minimize this is like a cost index. We minimize cost index, we have different solutions. For that, x2 equal to 2.5, x1 equal to 0. All right, that means that. So we minimize x1's absolute value plus x2 absolute value. That minimize 5 minus 2x2 plus x2. Because x1 equal to 5 minus x2. So we minimize those two, and we got a x2 is equal to 2.5. x2 is 2.5. And this is j. That's we call this, we minimize that. Now, if we minimize that, then we partial it, then our solution is x2 equal to 2 and x1 equal to 1. Solution is different. So you index, when you minimize, you have multiple solutions, when you minimize different objective function, like this minimize like that or minimize like that, then your solution is different. So when you have a multiple solutions, in many cases, we say we want to minimize something, so that we can get from that many solutions, we get some solution that's what we want. And why we want to do this? It's simple. If you look at this, absolute value x2 and absolute x1 add together is 3, so larger than 2.5. So you really can get any solutions. If you want to minimize that, you can get any other solution that's better than this. So this is like optimal control problem. So this is like index, and this is like index 2. So, but all this we call the cost index, they all must be positive. This is positive. Okay, and that is the solution of this one, x1 and x2. And this one's x1 equal to 0 and x2 equal to 2.5, and this is j. That's my cost index. That means I minimize different j, and this j is x1 absolute value plus x2 absolute value, and this j is x1 squared plus x2 squared, then square root of that. Okay. And this is minimum error solutions. Now, these equations, we know that they are parallel, so you don't have solutions. So we can, if we minimize the error, we want to say minimize this x1 plus 2x2 minus 5, that's the error, plus 2x1 plus 4x2 minus 6, that's absolute value of that, and that's the error. So minimize this equation error, that equation error, and or we minimize this square root plus that square root and square root of that, then you will get the solution like this. All right, for this one, you get solution partial that, you get multiple solutions, still multiple solutions. That means x1 plus 2x2 minus 3a equal to 0. The same thing for this one. So you still get multiple solutions. That means you get solutions somewhere between these two lines. And that solutions inside that line, that solution will minimize that. So there's a lot of things going on. So solution 1, if you minimize those, then x2 equal to 1.7 and x1 equal to 0. You minimize the x1 square root plus x2 square root from here. You also minimize this or minimize that, you got different solutions. All right. But either solution, none of the solution will satisfy these equations. All right. So this is linear matrix equations. I'm going to just quickly show the matrix equation. This is the matrix equation I already show you in the D-square solutions. So that 1, 3, 5, 1, 1, 1, 2, 1, 3, x1, x2. The solution is x1 minus x2 and 1, 3. If this change 5 to be 6, then no solution for x1. Now you know why there's a solution for this? Why there's no solution for this? Because those three equations are not independent. These three equations are not independent. But these three equations are independent, so there's no solution for this. But we can solve these square solutions. Although there's no solution of that, we can solve this square solution of this by taking the inverse of this, then we got x1 and x2. Right? So linear matrix equations, any matrix equation that are like this, we try to solve. Y is given, A is given, can we solve X? That's the matrix theorem. No. Now you gotta be careful of those no. Vector norm and matrix norm. The vector norm is absolute value of each element. X2 norm of 2 is mean square root sum I x2 I square. And this norm, infinite norm, is max I xi, the absolute value of that. And they all satisfy these equations. That means A alpha x equal to absolute alpha, a norm of x. If x not equal to 0, that means x norm always larger than 0. Any norm, they're always larger than 0. And x plus 1, y, the norm of that, doesn't matter which norm, they satisfy this. The norm of x plus norm of xy always larger or equal to x plus y norm. Okay, matrix the same thing. So this is the basic matrix theory, and that's matrix norm. This matrix norm, you gotta look at this matrix norm, and those matrix norm, in matter of fact, some of the norm related to singular values. All right. So all the control theory based on most of the control theory based on this, the vector wise based on this norm, and matrix wise based on this F norm. We call F norm. So most of the control theory or any other control problem, we all use the call this square root norm. That means Aij square and summation of all the element inside the element and square root of that, and matrix that always larger than 0. No. And they all satisfy this. You know, why the people in matrix theory, they want to develop this. They want to have this norm. You know, for compare, let me ask you, any two matrices, the same size, how do you compare it? Any matrix, two matrices, any two matrices, can you compare? No. There's no way you can compare the scalar, right? 2 rather than 1, we know that. and 2 larger than minus 3. We know that. But how can you compare a matrix? The only way to compare a matrix is to compute their norm. You can say, oh, okay, this matrix norm is larger than that matrix norm. So when you try to compare two matrices, then the only makes sense is to compare their norms. All right, you can compare the matrix C1 norm or F norm or infinite norm. The same thing vector, two vectors you cannot compare. Any two vectors, there's no way to compare these two vectors, which one is larger, which one is small. So that's why the mathematician developed the norm for the matrix of vectors to compare for comparisons. That's one of the major purposes. So don't ignore this kind of definition, because all the metric theory, all the control theory, also based on this kind of norm. Okay, example. Look at this. Vector 1 minus 2. The one norm will be absolute value at 1 plus absolute value of minus 2 equal to 3. The second norm of vector is 1 square plus parentheses minus 2 square equal to square root 5. Then the infinite norm is equal to the maximum of x1 or maximum of minus 2, the absolute value of minus 2. So this, of course, equal to 2. Look at that, they're all positive. For this case, which one is largest? That one is largest. This one is second. That one is third. But it's not always this order. In this example, the one norm is larger than the two norm, right? And two norm is larger than infinite norm. All right, matrix 1, 1, 2, minus 2, 3. All right, the maximum of summation I, that's the row. The I is row. So row add together. The absolute value of that. This is J, maximum J, and I is row. So I is like this, 1, 1, and 2, 1. So 1, 1, 2, 1. So that absolute value 1 and minus 2 is 3. Absolute value of 1 plus absolute value of 3 is 4. So 3, 4. And maximum of that equal to 4. The F norm will be square root of that 2. We have 2 divided by 1 square plus 2 square plus 3 square equal to square root of 15. And A infinite norm is, this is for column, and this is for row. So this row, 1 plus 1 equal to 2. This row, the 2 plus 3, because the absolute value of that, 2 plus 3 is 5. So this is 5. So which is largest? Infinite norm here, the matrix is largest. And the second one is what? Second one is this. And this is the third one. But this is not always that order. All right. I think this eigenvalue, we talk about that, and then I'm going to stop here today. There's about 5 minutes left. But this, because I have a few minutes left, I just review a little bit about matrix since, and that for you to understand it a little bit better for the matrix, the theory. All right. If you have any questions, you can ask. Other than that, and that's the end of this class. See you next week. I might go to NCU next week. That's my last time go to NCU. Our final will be 3 weeks away, I think. Yeah, this is second, right? The second, what by 21 plus 21, 23rd. So our final will be 23rd, June 23rd. And so we will have 3 weeks away, and 3 weeks away, and I have only 2 weeks to teach. So these next 2 weeks, I'm considering what is I want to teach so that I can finish in 2 weeks. And I will upload it anyway. So whatever I want to teach. Okay, all right, see you next week.
Give it a thanks.